Hey, calculus students. So we're going to start talking about vectors today, and it's just going to be kind of an intro to vectors. It might get a little bit long. It might turn into a two-parter here. We'll see. But anyway, let's go ahead and get started with vectors. And so just to kind of preface it, vectors exist in two-dimensional space and three-dimensional space. Yesterday in class, we learned about three-dimensional space. And so a lot of what we're going to do here with vectors is going to be applying them to three-dimensional spaces. But they do also exist and work in two-dimensional space. And they are used in science and engineering quite a bit, usually to denote forces and things like that. Vectors are useful because they have both magnitude and they have direction that go with them. And so here's some different ways that they can be denoted. Sometimes it'll be like with a bold letter. Like oftentimes in textbooks, you'll see a bold letter. That's the best I can do for bold with just my writing. So usually you're not going to see me use bold letters to denote vectors, especially if I'm just like writing on a board. The other way that you can denote them is a letter with an arrow above it. Sometimes your arrow, like older textbooks, might have arrows that look kind of like half an arrow like that. But those are some ways that you can denote vectors. You can also talk about them using their endpoints, kind of like a ray in geometry. So if this is your vector, we can call, vector v. It's got endpoints. You could also call this vector AB, kind of like a ray. And so some words you might see around vectors, the tail and the tip, so the starting point or the initial point and the terminal point. So that's some vocabulary you might see around vectors. And then vectors, like we mentioned, they've got both magnitude and direction. So if the vector has two vectors have the same magnitude and the same direction, that's what tells you that they're equal. Both of those things must be the same, so the same length and the same direction in order for the vectors to be equal to one another. Okay, so the first thing we want to talk about is adding vectors. That's what you're going to see a lot in the first part of this chapter. Where'd my eraser go? Here we go. All right. So with vector addition, if you're talking about it in terms of endpoints and things like that, we have this concept of vector AC is equal to vector AB plus vector BC. So if I've got 3 points, A, B, and C, this would be vector AB, this would be vector BC, and if I add those two together, the one that results is vector AC. So when you add vectors, you're going tail to tip. So the first one, I take the second one and I put the tail end next to the tip, and that gives me my new vector. Okay. And we'll see what this looks like when applied to a coordinate plane later on. But for now, we'll keep going with this. So you can add vectors. You can also multiply vectors by a scalar to basically give it a new length. So for example, if you've got, let's say we've got a vector v. Well, 2v would give me a vector that's twice as long. 1/2 v would give me a vector that is half as long. But what if I multiply it by a negative? What if we had negative v? That just changes the direction of the vector. So it's the same length, but instead of going this way, it now goes this way. Okay, so if we were talking about subtraction then, with vectors, kind of like we added vectors, now we can subtract them as well. That's just adding the negative version of the vector, right? So if I had two vectors, let's go, we've got vector u and v, and we'll say v looks like that. So if I wanted to go u minus v, that's just going u plus negative v. So if I had vector u, then I would switch the direction of vector v to make it like that. So here's u, here's negative v, and so then u minus v would be this vector. Okay. So we can add vectors, we can subtract them, we can multiply them to change their length. So now what we want to do is impose a coordinate system on our vectors and take a look at what that does. So if you're looking at vectors in a two-dimensional coordinate system, this might be, vector A, and it's at the point A1, A2 is the ending point. Then the vector would be written as A1, A2, but with arrow brackets so that it's different than just a coordinate point. So if we're expressing vectors by talking about in a coordinate system, we want to use arrow brackets instead of parentheses like we do for coordinates. Or if we're in three-dimensional space, this might be my vector A this time, and it's pointing at the coordinate A1, A2, A3. And so then the vector, we would say, equals arrow bracket A1, A2, A3. Okay. So again, we do that to differentiate between coordinates and vectors. And then, so a position vector is a vector that goes from the origin to a point. But if you want your vector to go between, or to be defined by 2 points, so this would be like a position vector. It goes from the origin out to a point. If you want your vector to be defined by 2 points, A and B, so let's say A is A1, or actually, let's go with X, Y, and Z. X1, Y1, Z1, and B, X2, Y2, Z2. If you want your vector going between those 2 points, then vector AB is X2 minus X1. Sorry, my dog was chewing something that he shouldn't be. Y2 minus Y1, Z2 minus Z1. So you would just take and subtract the coordinates, and that would give you the vector AB. Okay. So then another thing that we want to be able to do with vectors is talk about their length. So when we're thinking vector length, kind of think distance formula. So let me erase this. Let's look at that vector for a moment. If I wanted to find the length of vector A, first of all, we would denote the length using those kind of absolute value lines. And the length or the magnitude of vector A, or vector length is the square root of a1 squared plus a2 squared plus a3 squared. So it's just the x component, the y component, and the z component squared. And remember when we learned about the distance between points in three-dimensional space, it was kind of the same idea. It'd be like if one of your points was the origin. You'd be subtracting 0 each time from these before squaring them, so we just shorten it. So if you want to think distance formula when you're thinking of vector length, go for it. Okay, so then adding vectors, subtracting vectors, scalar multiplication of vectors. When we're in a coordinate system, would go about how you think they would. It's fairly intuitive, but let's talk about it. Okay, so let's say I have a vector A, A1, A2, A3, and a vector B, B1, B2, B3. Okay, so I can add those vectors. I can go vector A plus vector B, and that's going to give me A1 plus B1, A2 plus B2, A3 plus B3. And these are vectors in three-dimensional space. And we can do the same thing to subtract the vectors. Vector A minus vector B. So A1 minus B1, A2 minus B2, A3 minus B3. Okay, so same idea for subtraction. Or we could multiply by a scalar. Let's say the scalar is C. If we want to know what C times vector A is, we would just get CA1, CA2, CA3. Okay. And it would work the same way for two-dimensional vectors. You would just have one less term on each of your vectors. Okay, so we're going to end this video just listing the properties of vectors. So here we go. And again, properties of vectors, fairly intuitive, especially if you've, taken all the math classes you have up until this point. But it's good to know. With vectors, addition is commutative. So vector A plus vector B is equal to vector B plus vector A. Oh, and for these, we're saying that A, B, and C are vectors. And then D and F are scalars. Okay. So D and F are just numbers. A, B, and C are vectors. Okay. You can group the terms however you like. You could go A plus parentheses vector B plus vector C. And that's going to be the same thing as parentheses vector A plus vector B plus vector C. So it doesn't matter the order that you add them in again. Let's see. Vector A, if you add 0, it's still the same vector. That's, comforting. If you add the opposite of a vector, so if you go vector A plus negative vector A, you do get 0. So that's also good. You can, do and undo. Let's see. The distributive property holds with scalar multiplication and vectors. So if you have a scalar and you multiply it by vector A plus vector B, that's the same thing as D times A plus D times B. So that's good. Let's see, what else do we have? Oh, it holds, you can distribute a vector into some added scalars. So, let's see, running out of room here. So if you had d plus f times vector a, that's the same thing as dA plus FA. Okay, and let's see, we have two more. It doesn't matter how you group the multiplication of scalars and vectors. So if you have d times f times vector a, that's the same thing as d times f times vector a, parentheses grouped that way. And then lastly, if you go 1 times vector a, that is still just vector a, as you would hope it would be. Okay, so that's everything we have for vectors for this video. I will make one more talking about some other things with vectors like standard bases and unit vectors and things like that, but that's all for now.